Hi there. So in this section, we're going to focus on rational functions and more specifically, all of the components that come together to form the graph of a rational function. We've spoken loosely about asymptotes and holes in your graph, but we haven't actually talked about how you calculate those asymptotes and holes in many cases. So we'll be nailing that out in this particular section, along with bringing into some old terms. As Math 171, things don't just go away. We'll bring back in domain, as well as x and y intercepts, and I think those are the older topics that you're used to, okay, already. All right, so let's go ahead and get started here. So your rational functions are just a quotient of two polynomial functions. So r of x equals p of x over q of x. Of course, denominator cannot equal 0, so that bottom piece there, q of x, cannot equal 0. What will the domain of these functions be? And hopefully you recall from our prior sections when we talked about domain that your domain would be all real numbers except where the denominator equals 0. Okay, so those would be the values that we would have to exclude, is anywhere your denominator equals 0. So these next four examples here, I say find the domain of our rational functions. This is really just a throwback review from what we did back in the first unit when we were talking about domain, but it's important as we move into this section just to kind of revisit that. So that's what I had put it up here at the top of our notes. If I want to find the domain of the first piece, then if you remember when we first started talking about domain, if you have a denominator, then you automatically have the potential for something to be excluded from your domain. And so what we did back then was we took our denominator and we said, okay, well, that denominator cannot equal 0, and we solved for x, and that told us what our domain was. So from here, we would just add 2 to both sides, of course, and so we would have x cannot equal positive 2. Meaning then my domain can be everything but positive 2. So to write that in interval notation like we did before, we would say negative infinity to 2 united with 2 to infinity. That would be our domain. Okay, we'll move on to example 2 over here. If I take this denominator, x squared plus 1, I say, okay, you cannot equal 0, because if it does, it would be undefined. Solve for x, so we subtract 1 from both sides. We get x squared cannot equal negative 1. And then one more step, we take the square root of both sides. We learned in the last unit that the square root of negative 1 equals, this cannot equal, plus or minus I. We're not going to be able to see I on our graph, so therefore we don't have any exclusions. There are no exclusions in this case. And your domain is going to be all real numbers, or negative infinity to positive infinity. Okay. And how about we do one more together here? Here in example 3, I have x minus 3 over x plus 3, x plus 1. Since I have 2 pieces in the denominator, I set both of those not equal to 0. Solve for x, so we'll subtract 3 over here. We find out, okay, x cannot equal negative 3. Over here, we subtract 1 from both sides. We find out x cannot equal negative 1. So we're saying that our domain can equal any value but these two. So if you think about their placement on a number line, here's your negative 1, here's your negative 3. It can't equal either one of those values. So we're going to write then negative infinity to negative 3, then negative 3 to negative 1, and then 1 to infinity. That would be our domain. Let me go back and put my little unions in there. Okay, that would be our final domain. I'll let you try number 4. Very straightforward. All right, now let's start to begin our discussion on asymptotes. Asymptotes are lines your graph approach but rarely touch, and you won't be able to see them in your calculator, but a vertical asymptote is just that, a vertical line. And here would be, hold on just a second, let me move this back so things don't get, all right, that looks okay. All right, so here's an example. Here, I'm just making you, I'm drawing you a graph to give you an arbitrary example of a vertical asymptote. So this dashed line here is the vertical asymptote, and then the graph itself would come up and basically hug that asymptote, but it doesn't cross it, okay? And likewise, then we say down here, lines that your graph approach but rarely touch, okay? Vertical asymptotes a graph will never cross a vertical asymptote. It's not possible, so that's why we say, I always like to use the word that it hugs the asymptote, okay? Gets really close to it, but it never touches it. Horizontal and oblique asymptotes, we'll talk a little bit more about in just a moment. A graph can cross a horizontal or an oblique asymptote, but it doesn't have to, okay? And it's also pretty rare, okay? Just below that, finding your vertical asymptote. So we'll focus on vertical. And so for our vertical asymptote, you're going to factor both the numerator and the denominator. You will cancel out any factors, meaning basically it's like reducing. Holes occur for any factor that cancel out. So if you end up being able to cancel something out, then you have now created a hole. To find the coordinate of that hole, which you have to do, you plug the x value. You're going to be fine. You'll be fine. You'll know where the hole is. You're going to plug that value into what we're going to refer to as, the reduced function. Then after that, you'll set your denominator equal to 0 and solve for x. Anything left over, then those are going to be your vertical asymptotes. This will make more sense as we work through a couple of problems. So let's come down here in example 1 and 2. We're finding our vertical asymptotes and our holes. Okay. So the first thing it says is factor numerator and denominator. So if I'm looking here in example 1, I can't do anything with the top, but on the bottom, hopefully you recognize this as a difference of squares. We can take the square root of x squared. We can take the square root of 4, and there's a minus sign in between. So square root of x squared, x and x, square root of 4, 2 and 2. The signs are always a plus and a minus. Now here, it says then reduce. You're canceling out anything that you can. Remember, when you're canceling out, it's not legal just to cancel out these x's. You have to take them as pairs. Okay, so I would have to be able to cancel out a full x plus 2 or a full x minus 2. I can't here. So since nothing is canceling out, I don't have any holes in this example. So to move on from there, then it says, okay, well, if you're not able to cancel out this, and also I wasn't able to reduce, this would also be known as your reduced function. Okay, you're going to set the denominators now equal to 0. So I'm setting x plus 2 equal to 0 and x minus 2 equal to 0, and solving for x in both cases. So I subtract 2. I get x equals negative 2. Add 2 over here. And I get x equals positive 2. These are my two vertical asymptotes. So let me label right here that I have a vertical asymptote at x equals negative 2 and x equals positive 2. Just to let you know, like if you were now to put this graph, that function in your calculator, y equals x over x squared minus 4, and also be sure when you put this in your calculator, rational functions, I always recommend put the top in parentheses divided by the bottom in parentheses. Technically on this one you only need the bottom, but it's easier just to say always put top and always put bottom in parentheses. It's telling us that I have vertical asymptotes at positive 2 and negative 2. So I'm going to put in those vertical asymptotes. And if you were to now go to your calculator and have it graph this function for you, in which we're going to be doing this by hand here in a few moments, but for the moment I'm just going to use my calculator, and you would see that you would have a graph that looks like this. So you can see that in all of, we've already calculated domain before. Remember, domain is where your denominator can't equal 0. Denominator can't equal 0. Those also are corresponding to vertical asymptotes. Think about what your domain would be. You'd say negative infinity to negative 2, negative 2 to positive 2, and then 2 to infinity, right? So the correlation between your vertical asymptotes and your domain now are hopefully coming together. And then notice how my graph is always hugging those asymptotes in each case. Okay. All right, let's scoot on over here to example 2. Again, first step tells me to factor both numerator and denominator, so we'll do that. Up top is a difference of squares, so I can square root of x squared, x and x, square root of 9, 3 and 3, a plus and a minus. On the bottom, factor this. Do a little guess and check here. The only way to multiply to give you x squared, x times x. Most common way to multiply to give you 21, 7 times 3. You want a positive 4 in the center, so which number are you going to need to make positive? Hopefully you agree. It had to be 7, right? Because you would have 7x on the inside and negative 3x on the outside, so 7 minus 3 will give you that positive 4. Now, your next step said to reduce. In this case, we can reduce. Notice here you have an x minus 3 up top and an x minus 3 on the bottom. So when I cancel those out, my reduced function now is x plus 3 over x plus 7. And I'm going to label that up here for you as, this is what's known as your reduced function, because the reduced function is going to be playing a large role as we move forward here in a few moments. So this is referred to as your reduced function. Since you had a factor cancel out, those steps above told you, okay, that indicates that you have a whole at this particular value. So if you set that x minus 3 equal to 0 and solve for x, hopefully you're tracking with me that that would be x equals 3. So I have a whole at 3. And to find the y value of my whole, that's what my directions up here were saying. To find the coordinate of your whole, plug the x value into the reduced function. So I'm going to come right here and I'm going to plug 3 into this reduced function. So it will look like this: 3 plus 3 over 3 plus 7. And so that gives me 6 over 10. And then that can be reduced. Divide them both by what, 2? So 3/5. Okay. Now from here, so you've established that you have a whole at 3/5. I'm going to box that in for us. We have our whole at 3/5. Now to figure out if we have any vertical asymptotes, we look at our reduced function, set now our denominator equal to 0, and solve for x. So I set x plus 7 equal to 0, solve for x. So I subtract 7, x equals negative 7. So now I know that I have a vertical asymptote at x equals negative 7. And just to let you know here, to kind of give you another, if we consult our calculator and put this function in, now on this one you would have to put top in parentheses divided by bottom in parentheses. We know that we have a vertical asymptote over here at negative 7. Your calculator is not going to show this dashed line that I'm drawing in. Okay, you'll kind of see it as like an imaginary kind of space on the calculator screen that your graph is approaching but not touching. The other thing that your calculator will not show you, it is not going to show you a whole. You can find it in the table on your calculator, but you're not going to be able to see it physically on the graph. Okay, so that's why it's important for you to actually find them. And our whole here is at 3. Make this smaller. 3/5. And so 3/5, very small number, so like right there. Okay, but I need to make it like a whole. There we go. All right, now I'll just draw my graph, and I'm just at the moment I'm just consulting my calculator to get this graph. Okay, so it looks like this, and it looks like this. Okay. Well, that's the idea. Okay, again, calculator kind of gives you a blank space to show you where your asymptote is, but it will never show you a whole. Okay. All right, well, let's flip it on over. Next page. Let's look now into our horizontal asymptotes. Horizontal asymptotes are associated with the degree, okay? And it has to do with the degree of your numerator and denominator, so you'll always be looking at top and bottom. When the degree is the same for the numerator and the denominator, meaning you've got this example here where ax to the n over bx to the n. A and b are just numbers, and this is x to the nth power, so the degree is the same, this n on top and bottom. The horizontal asymptote is always the line y equals a over b, meaning you're just taking the coefficients in front of your x to the n's, okay? So the example that I gave you down here below, if you have y equals 2x squared minus 9 over 3x squared plus 2x, notice here you've got the same degree on top and bottom. So then my horizontal asymptote would just be the line y equals a over b 2/3. Final answer. Okay. Example 2, because there are 3 cases then. You think about if you're looking at the degree, there's going to be 3 cases. Your degrees can be the same. Case 2, the degree of the numerator is less than the degree of the denominator. So when that happens, you have a horizontal line as the line y equals 0. Example that I gave you here, the degree of the top would just be 1, the degree of the bottom was 3, so the degree of the top is less than, so therefore we just say, okay, here my horizontal asymptote is just the line y equals 0. And then the last case would be when the degree of the top is more than the degree of the bottom. In that particular case, your rational function does not have a horizontal asymptote. The way I help myself remember this case is think about if the degree of the top is bigger than the degree of the bottom, which you see here in this, I think of it as being top heavy. So when your degree is top heavy, that implies no horizontal asymptote. And that's exactly what you see here, that the degree of the top is larger than the degree of the bottom, so it's top heavy, and you would say you have no horizontal asymptote. The top heavy part, you wouldn't write that, of course, but I mean that's the way that I help myself remember. Okay, well if I'm top heavy, that's when I don't have one. When they're the same, that's easy. Just pluck off the coefficients in front, and then the other case is just y equals 0. Okay. All right, so from here, just below that, we talk about what are referred to as oblique or slant asymptotes. They mean the same thing. It just depends on what you maybe have heard in the past, or maybe you haven't heard either one. I think I typically say oblique asymptote, but maybe slant might even be a better description of what a oblique asymptote is. And a horizontal, a vertical asymptote goes up and down. A horizontal asymptote, of course, goes across. An oblique asymptote is always a linear line, meaning it's going to have like a slope and a y-intercept, okay? So an oblique asymptote is always something that looks like that, okay? Just below down here, I give you a fact. A function cannot have both a horizontal and an oblique asymptote, okay? So just so you're aware of that, you cannot have both a horizontal and an oblique. Obliques only occur, though, so they're pretty, in terms of when they can occur, they can only occur when the degree of the numerator is 1 more than the degree of the denominator. Okay, so it's that case where you're top heavy, but you can only be top heavy by 1. Okay, so I'll write that for you. Essentially, it's saying here to have an oblique asymptote, you can only be top heavy by 1. Only be top heavy by 1. So here, the example that I gave you, I say, well, let's find the oblique asymptote for that previous example, because you notice here, oh, I was top heavy, but I was only top heavy by 1. This is x squared, and this is x, okay? So this graph is going to have an oblique asymptote. Just to do a quick little jaunt here. If I had y equals, let's say, 4x to the 4th minus 1 over 2x minus 3, I'm top heavy, so I'm not going to have a horizontal asymptote. I'm top heavy by more than 1, so I'm not even going to have an oblique either. Okay, so just that's what we mean by having an oblique. You can only be top heavy by 1. This is degree 4, the bottom is degree 1, so I'm more than 1 off. Okay, so this one would have no horizontal and no oblique asymptote. Okay, just a little aside there for you. All right, so now let's come back over here. It wants us to find the oblique asymptote. Unfortunately, the only way to find an oblique asymptote is to use long division or synthetic division. Remember, you can only use synthetic division if you don't have a number in front of your x. So here we're forced to use long division. So we use our long division. I have 2x plus 3 going into the 4x squared minus 1. So I have 4x squared. I'm missing my x term, so I'm going to put 0x minus 1. And now I just work through my long division. I've done before, so we say 2 times what gives us 4? That would be 2. I've got 1x, but I need another x, so that would be 2x. 2x times 2x, 4x squared. 2x times 3, positive 6x. Draw your line, change your signs. So those 4x squares cancel out. Now I'm left with negative 6x minus 1. 2 goes into, or 2 times what gives you negative 6? That would be negative 3. You've got an x. You needed an x, so you don't need to put anything else there. Negative 3 times 2x, negative 6x. Negative 3 times positive 3, negative 9. Draw your line, change your signs. 9 minus 1, of course, gives us 8. That remainder down there means nothing. All that we need to focus on is this piece right here. That is our oblique asymptote. So we have an oblique asymptote, and it's the line y equals 2x minus 3. Okay, so think about then for this particular graph, you have 2x minus 3, so we know negative 3 y-intercept. And then from there, I'm going up 2 over 1, up 2 over 1, kind of something like that. That would be your oblique asymptote for that particular graph, okay? And then we could find our our vertical asymptote by setting the denominator equal to 0. So if I set that denominator equal to 0, 2x plus 3 equal to 0. I'm taking this a little further just so you can kind of see what the graph would look like. If I find my vertical asymptote here, like we said on the front page, set your denominator equal to 0 and solve for x. So subtract 3. 2x equals negative 3, so x equals negative 3 halves, so that's negative 1.5. So here's your vertical asymptote, like that. And then if we go to graph this in our calculator, I think we're going to have to adjust our window, but I think it's worth showing you that. So if I go into y equals, and up top I'm going to put in my 4x squared minus 1 divided by, on the bottom, I have 2x plus 3. Hit graph. So here you can kind of get the idea of, okay, there's definitely that oblique asymptote. I'm going to go back to the graph that I've drawn for you, though, so you can see that. Here we go. You can see that your calculator is showing you this portion of the graph. Okay, something has to happen in one of these other portions over here. So I need to adjust my window to figure out where the rest of my graph is. Okay, you know, is it over here in this quadrant? Is it over here? Is it down here in this little triangle? So I'm going to go back to my calculator. Let's adjust my window. Let's see more of the lower portion of our y. So let's go down here and let's make y, let's go maybe negative 75. 75. Okay, hit graph. Let's see what happens. There you go. So there you're able to see it then. So then you can tell, okay, from there, I wonder if I can maybe I can go back to my window, not have to make it quite that big, and maybe go, let's say negative 25. There, that's even better. So you have that. We know that that negative 1.5 is right here. So go back to my graph. There's my negative 1.5. And actually, it looks like it is down there in that little triangle piece, isn't it? Yeah, because if this is our asymptote through there, it won't let me draw on there. If that's my asymptote through there, and there's my other asymptote, it is below that. So it is down here in this little spot. I just drew my graph a little bit so it's harder to see, but it's down there in that little spot there. Okay, we're gonna nail that down, okay, here in a few moments, but I just wanted to kind of revisit a little bit there. Okay. All right, so just down here below, I'm asking you to find your horizontal and oblique asymptotes. So you're focusing on your degree. In example 1, notice how the degree of the top is less than the degree of the bottom. So since it's less than, that's the line y equals 0. So that means I have a horizontal asymptote at the line y equals 0. And remember, as I mentioned a minute ago, I've got this fact up here. Remember, you cannot have a horizontal and an oblique asymptote. Okay, you can only have one. Okay, you can have vertical. You can have vertical in one or the other, but you can't have horizontal and oblique. Scoot over to number 2. Notice here, degree is 2 on top, degree is 2 on the bottom. So since the degree is the same, then I'm going to have a horizontal asymptote at the line y equals. Pluck off those coefficients, 8 divided by 4, and we can reduce that. We know then we've got a horizontal asymptote at the line y equals 2. All right, scoot on down to number 3. Notice here that the degree of the top is bigger than the degree of the bottom. So since it's top heavy, we know that we have no horizontal asymptote. To have an oblique, you can only be top heavy by 1. Notice here we're top heavy by 2. So that also means we have no oblique asymptote. We don't have any horizontal or oblique asymptotes in that problem. This last example, example 4, we're top heavy, so that tells us we have no horizontal asymptote. But this time we're top heavy by just 1, right? Degree at the top is 2, degree on the bottom is 1. So since we're just top heavy by 1, we do have an oblique asymptote. We can do long division or synthetic division. Here, because I don't have a number in front of my x, it actually permits me to do synthetic division. So when you can do synthetic division, personally, that would be my choice. So remember, take the opposite of the factor down here. So that would be a positive 2 out in the box. Line up your coefficients. 2, negative 3, negative 1. Remember, above the line, you add or subtract. Below the line, you multiply. Always bring down the first term. 2 times 2 is 4. Add together. We'll give you 1. 2 times 1 is 2. Add together. That'll give you a positive 1. Again, we don't care about the remainder. We just care about these coefficients here. It's always a degree less, so this is 2x plus 1. So that tells us then that we have an oblique asymptote at the line y equals 2x plus 1. Final answer. No horizontal, but you do have an oblique. All right, so let's flip it on over. Next page. Here's where we are going to put everything together in terms of your domain, your holes, all those asymptotes, x and y intercepts, and to be able to generate a graph of this rational function without using our calculator. Okay. In Blackboard for your course, I've given you a quick reference guide. I encourage you to maybe keep this handy here because it puts everything in one spot and tells you how to find everything. Okay. Right, so you always factor your numerator and denominator. You state your domain. Remember, you exclude any values that make your denominator equal to 0. Reduce if possible, and then everything else you find using the reduced function. Okay, so use the reduced function to find your vertical asymptotes. That's where you set your denominator equal to 0 and solve for x. Remember, holes occurred whenever you were able to cancel out and actually create a reduced function. And you find that particular point by plugging that x value into the reduced function. Horizontal and oblique asymptotes, remember you're looking at your degree. Your graph can cross a horizontal and oblique asymptote. To find that cross point, you would set the original function equal to the asymptote and solve for x. We won't go that far here in this section, but for those of you going on to calculus, you would take it further like that. So I just went ahead and added that in here just so you would know that's how you find out whether it crosses or not. But we won't add that element here. And then below that, x and y intercepts, we've been doing these for so long now. Hopefully this is second nature. If you want the x-intercept, you let y equal 0 and then solve for x. For a rational function, though, you really only have to worry about setting the numerator equal to 0 and solve for x. Your y-intercept, you're plugging 0 in for x and cleaning it up, okay, solving. And then you'll be able to graph. Every once in a while, you have to substitute in an extra point to figure out, where the graph is in that particular quadrant. But by and large, you should be good to go with all of these pieces. So let's go back to our notes. And I'm actually going to look at all 4 of these examples with you, as I think they're all just a little bit different and show you different things, and it'd be good to, I think, for you to see the full instruction here. All right, so in example 1, they want us to graph the rational function by finding the domain, holes, asymptotes, x and y intercepts, basically all these pieces over here. So as we mentioned on the previous page, first thing you want to do is you want to factor it, try to reduce it if you can, okay? So up top, hopefully you recognize, well, hey, both of those terms, they have a 2 in common. Let's factor that out. And that leaves me with x squared minus 9. And you know what, while we're here at the top, let's just keep going. We can fact x squared minus 9, that's a difference of squares. We've already factored it here in this video, right? X plus 3, x minus 3. All right, we'll come down to the bottom, factor that. On the bottom, only way to multiply to give you x squared, x times x. Only way to multiply to give you 3, 1 times 3. And then from here, to get a positive 4 in the center, so you've got a 3 and a 1 to get a positive 4. You have to make them both positive. So now on the bottom, you have x plus 1 times x plus 3. From here, find your domain, okay? So before you're doing any kind of canceling, find your domain. So Find our domain. Remember, your domain are all real numbers except where your denominator equals 0. So we set x plus 1. We say it can't equal 0. And we say x plus 3 cannot equal 0. Hopefully you're getting good by now. Hey, if I want to solve for x here, I'm just subtracting 1. So x cannot equal negative 1. Over here, I'm just subtracting 3. So x cannot equal negative 3. So to find my domain, then we're going to say, okay, well, it can't equal these values. And I might be revisiting a problem that was already in your notes. Negative infinity to negative 1, negative 1 to negative 3. It's a similar problem. And then negative 3 to infinity. You know what? I just did that. Sorry. No, I was not thinking about this in order. A number line, right? Shoot. Negative 1, negative 3. So I can't equal these values. So negative infinity to negative 3. Sorry about that. Then negative 3 to negative 1. Then negative 1 to infinity. There we go. All right. Now, from here, we figure out our reduced function. So if we go back and look at our function here at the top, notice if are there any values that we can cancel out. Hopefully you agree. There are. Those x plus 3s, they can cancel out. Since you were able to cancel out, let's go ahead over here. Let's do it this way. 2 parentheses x minus 3 over x plus 1. I'm going to box that in. And I'm just going to write reduced underneath it. That's your reduced function that we're going to be using for everything else down here, okay? All right. Wholes, remember, occur for any factors that are able to cancel out. So in this particular case, I do have a whole. We were able to cancel out. I have a whole. I was able to cancel out that x plus 3. So if you set that equal to 0, then you would have x equals negative 3. So you have a whole at negative 3. To find the y value of that whole, you plug it into the reduced function. So it'll look like this. 2, and then you're plugging in negative 3 minus 3 up top. And then on the bottom, negative 3 plus 1. Just clean up. Parenthesis turns into what? Negative 6. On the bottom turns into negative 2. Just keep cleaning up top, negative 12 divided by negative 2. Gives us positive 6. So negative 3, 6, we are going to have a whole on our graph. So let's write that over here. Negative 3, 6, we have a whole. All right, now let's visit vertical asymptotes. Going to reduced function. Remember, vertical asymptotes you find by setting your denominator equal to 0. Again, if you need it, pull this little sheet out. Okay, look back at your notes, whichever way you want to look at that. Get back to, sorry. All right, so setting your denominator of your reduced function equal to 0. So I set x plus 1 equal to 0. Solve for x. Just subtract that 1, so x equals negative 1. Okay, and then we want to look at finding our horizontal asymptote. Horizontal asymptote, technically, you can go back to the original function or the reduced function, whichever way you see best. In the reduced function, you have 2x, right? Because if you were to distribute that 2 through, you'd have 2x, and on the bottom you have an x. So the degree at the top is the same as the degree of the bottom, and the coefficients would be 2 over 1. So you have a horizontal asymptote at the line y equals 2 over 1, which is just 2. So horizontal asymptote, the line y equals 2. Horizontal and oblique asymptotes are lines, so they should be x equals and y equals. Okay, an oblique asymptote is a line, so it should be y equals. Okay, and I'll say this as well. If you want to go back to the original function for the horizontal asymptote, absolutely you can. Degree is the same on top and bottom. Take your coefficients, the same coefficients, 2 over 1. It will always be that case. Okay. X-intercepts. Oh goodness, go away. Sorry. X-intercept. So to find your x-intercept, that little sheet told you that you are setting your numerator equal to 0. So your numerator here, and you're just looking at your reduced function. So you have 2, it might be easier. Actually, let's just do it how we've done it all in the past. 2 parentheses x minus 3, and then you'll see why it's just the numerator. Typically, whenever we found x-intercepts, we let y equal 0 and solve for x. Well, think about it. If you were to now solve for x, you'd cross multiply. So 1 times the top is just going to give you the top. That's going to be 2 parentheses x minus 3. And then on the bottom, x plus 1 times 0 is still 0. So that's why I said on my sheet, the review guide there for graphing these, is that you always, when you're finding the x-intercepts for rational functions, you just end up setting the numerator equal to 0 and solving for x. Definitely use your reduce function here. So now from here, just distribute. So 2x minus 6 equals 0. So from here on out, it's never going to change. It will always be you set the numerator of the reduced function equal to 0 and solve for x. Okay, you don't have to set the whole function, but I just thought it would be easier to kind of make that connection for you. So it did look like magic. Add 6 to both sides. We have 2x equals 6. Divide by 2. So x equals 3. So I'm going to be crossing the x-axis at 3, 0. To find my y-intercept, let's write that. The y-intercept is 2 parentheses x minus 3 over x plus 1. Yeah, x plus 1. I'm just picking that reduced function. Okay. And you remember, for the whole semester, whenever we found y-intercept, we let x equal 0 and we solve for y. That's exactly what we're doing here. We're letting x equal 0. So everywhere I see an x, I'm plugging in 0. So up top I have 2 parentheses 0 minus 3. On the bottom I have 0 plus 1. I'm just going to burn a few steps here. 0 minus 3 in parentheses just gives me negative 3. On the bottom I have 1. So that gives me negative 6 divided by 1. Of course, that's negative 6. So I'm crossing the y-axis at negative 6. X and y intercepts are points. Okay. All right. So now let's graph these pieces on our coordinate plane here and see if we can't generate a graph with this information. So we have a hole at negative 3, positive 6. So negative 3, positive 6. There's my hole. And put that in. I have a vertical asymptote at x equals negative 1. My vertical asymptote. I have a horizontal asymptote at y equals 2. There's my horizontal. I cross the x-axis at 3. And I cross the y-axis at negative 6. Okay. These graphs, you cannot be in all 4 of these quadrants. Okay. So from the points that we see here, we can only be in 2 of them. From the points that you see here, your graph then is forced. We know it has to pass through these x and y intercepts and hug the asymptotes. So sure enough, this is what it's going to look like. That's the first graph of, one part of the graph down here. Then the other part of the graph, since you know that you have a hole up here, then you know you are going to be coming in and approaching that hole but not touching it, and then likewise approaching those horizontal and vertical asymptotes and not touching those. And that's your graph. Okay. It's going to take practice with these. There's a lot going on. Okay, let's do another one. Here in example 2, what might be a good idea for you: first, stop the video, make sure you can factor that. Okay, make sure you could get the whole reduced function. And this probably would be a good one to try solo from what I've just shown you. There's not too much different going on in this one until the very last step, okay, for the graphing part. So if you want, why don't you try to go as far as you can here in example 2. All right, so I'm going to just draw myself a little line here to keep things separate. All right, so for this particular function, I am going to first start by factoring numerator and denominator. So up top, only way to multiply to give you x squared, x times x. Most common way to multiply to give you 10, 5 times 2. We want a positive 3 in the center, so which number do you have to make positive? It has to be that 5, right? 5 positive, 2 negative. On the bottom, only way to multiply to give you x squared, x times x. The only way to multiply to give you 2, 1 times 2. And then We want a positive 3 in the center, so we would have to make them both positive. You'll notice here nothing's going to cancel out, so this will end up being your reduced function as well. To remember to find our domain. Oh goodness, sorry, this drives me nuts. Sorry. Okay. To find our domain, we set our denominators not equal to 0, so x plus 1 can't equal 0, x plus 2 can't equal 0. We solve for x, we pull that 1 over, so now we find out x can't equal -1. We pull that x over, we find out, okay, pull the 2 over, we find out x cannot equal -2. So I don't goof this domain up again. Let me draw it on the number line. So I have, here's -1, here's -2. We can't equal either one of those values, but we can equal everything else. So my domain, -infinity to -2, -2 to -1, -1 to infinity. Go back and put in my u's. Unite all of those pieces together. There's my domain. Remember, holes only occur when you have factors to cancel out. I do not have any factors canceling out here, so I do not have any holes. I'm just going to put a line through it. Vertical asymptotes. You take your reduced function. I'm going to box this function in up here because it's your function is your reduced function. You couldn't do anything with it. Okay, so that's be the function that we're going to use for everything else here. Vertical asymptotes are found by setting your denominators equal to 0. Well, really we've already done that, but I'll do it one more time here, as we just did it with our domain, right? That, get back a different color. X plus 1 equals 0, and x plus 2 equals 0. We'll pull that 1 over, so we know x equals -1. Pull that 2 over, x equals -2. So I have two vertical asymptotes, x equals -1 and x equals -2. You need to have those x equals in front there, okay? They are lines. All right, horizontal asymptote. Horizontal asymptote, you look at the degree. This was probably easier to go back to the original function. The degree of the top and the degree of the bottom are the same. So remember, when that happens, we just pluck the coefficients in front. So 1 over 1 just reduces to 1. So I'm going to have a horizontal asymptote, y equals 1. Again, it's a line. It needs a y equals in front of it. X-intercept, we talked about it in the last problem. All that needs to really happen here is that we set the top equal to 0. So your top is x plus 5 times x minus 2. All right, because there's your reduced function. Just use your reduced function here. Set that equal to 0 and solve for x. So hopefully you agree. If I set that first term equal to 0, I'm going to have, and solve for x, I'd get -5. If I set this term equal to 0 and solve for x, I'm going to get +2. So I have two x-intercepts. I'm going to be crossing the x-axis at -5 and at +2. Okay. And then lastly, for our y-intercept, you are plugging 0 in for all of your x's. I'm going to go back to this reduced function as well again here. So up top I have 0 plus 5, 0 minus 2, because remember, all y-intercepts are always 0, comma, and you're solving for your y. So I'm plugging 0 in for x. 0 plus 1, 0 plus 2. Starting to clean this up. Up top, you get a 5 in that first parenthesis, -2. 1 times 2 down here. Still clean up. I've got -10 over 2, which will give me -5. Got y-intercept at -5. X and y-intercepts are points. You should write those as ordered pairs. All right, so now let's start plotting these values that we have just calculated here. So we have vertical asymptotes at -1. Down here just a little bit. There's -1, and I also have a vertical asymptote at -2, so it's real close together here. And I have a horizontal asymptote at y equals 1. And let's plot these x and y intercepts. So I'm crossing the x-axis at -5. and positive 2. And I'm crossing the y-axis down here at negative 5. Now, if I go through and I plot, you can tell over here in this first piece that I have crossing, since I'm crossing the x-axis down here at negative 5, and that tells me that my graph is down here below that horizontal asymptote, like so, and hugging both of those, the horizontal and the vertical asymptote. We'll skip the middle section here for a moment, and then let's come over here to the to the right of that negative 1, and you'll see you've got an x-intercept and a y-intercept. So the graph cannot be up here, it's got to be down here and pass through these particular points. So here we are. Your domain, if you go back and look at your domain, remember your domain said that you were from negative infinity to negative 2. We've got that leg of the graph accounted for. Then it said that there's something between negative 2 and positive 1. If you notice on your graph, we don't have anything graphed here in this small space here. That's something we're missing. And then your graph goes from negative 1 to positive infinity. So that's the last piece here. Essentially what needs to happen is we need to figure out what's happening between negative 1 and negative 2. In order to do that, you need to just test a value. Okay, so a number, but you can't use negative 1 or negative 2, so unfortunately we've got to use a little decimal. So I just let x equal, I think the easiest value here would be negative 1.5. And take that negative 1.5 and plug it into, you can plug it into either form here. Oh, goodness. Everything got off. How bad did it get down here? Oh my goodness. I'm going to pause it a second. Let's see if I can fix this. All right, sorry about that. Thanks for your patience. Although it's really you didn't have to be patient. It's trying mine. Anyway, so please. Okay. We're trying to figure out what is happening between these two vertical asymptotes. I need to choose a value. I said choose negative 1.5. Take that negative 1.5 and you can plug it into the original function or the reduced function, either one. I'm just going to tell you, when you plug in that negative 1.5 into either one of those functions, oh my goodness. You are going to get a y value of 49. So what that tells me then, pen back, is that at negative 1.5, then my y value is up here at 49. And so we know we have to hug those asymptotes. So it's like you have a little mini parabola up there, okay, in between, so that you get your full domain, right? Because we knew our domain had to, we needed a part of the graph between negative 2 and negative 1. And so we know that negative 1.5, 49. Of course, this is not to scale, okay? We're saying this point right here is 49, okay? But I've run out of room. I can't, make it to scale at this point, okay? All right, let's flip it over. See if I can keep this computer under wraps so I can finish this up. All right, so here in number 3, we are looking at another rational function. We want to graph it here. We usually try to factor. Unfortunately here, there's not any factoring that can be done. On the bottom, you've got a plus sign. So because it's a plus sign, you cannot factor that any further. So you go straight away to finding your domain. This will be your original function. It'll be your reduced function. So to find your domain, remember you set your denominator equal to 0. Or you actually say your denominator cannot equal 0 and solve for x. So here we get x squared equals negative 4. We know we cannot take a number and square it and get negative 4. We're only going to get imaginary solutions. So as we talked about previously then, our domain here will just be negative infinity to positive infinity. You will have no exclusions. No exclusions. So negative to positive infinity, all real numbers. All right. Since you're not able to do any canceling out here, you also do not have any holes in this graph. Vertical asymptotes, so remember, vertical asymptotes, as found by setting your denominator equal to 0, x squared plus 4 equal to 0. Solve for x, we get x squared equals negative 4. If you try to take the square root of both sides, I'll go ahead and do it on this one. We get x equals, we know the square root of 4 is 2 because it's a negative, it's plus or minus 2i. So we do not, what that means then is that we don't have any, those are imaginary, so we have none. So we don't have any vertical asymptotes either. Horizontal asymptotes, remember, have to do with your degree. Here the degree of the top is less than the degree of the bottom, right? Because this has 0 x's and this has 2, so since it's less than, that's the line y equals 0. Go back and look at those, that portion of the notes. To find your x-intercepts, remember, it's just setting the top equal to 0. So setting the top equal to 0 here, you're not going to be able to solve that. There's nothing to solve for. So that means here we have no x-intercept. So none there. To find your y-intercept, we are going to let, remember y-intercept, we let x equal 0 and we solve for y. So we have 8 over 0 squared plus 4. 8 over 4, which is 2. So I have a y-intercept at 2. All right, so now we didn't get a lot from here, but actually you will end up having enough that you have a horizontal asymptote at the line y equals 0. The line y equals 0, it just happens to be the x-axis. Let me use a color that will kind of show up a little bit better here. The line y equals 0 is the x-axis here. That is the line y equals 0. That's your horizontal asymptote. So, and then you know that you have a y-intercept up here at 2. So you got to pass through that point, hug these asymptotes. So your graph is then going to have to look like this. That's it. Okay. So just wanted you to see that you don't have in terms of that asymptote, you got to be above it or below it. You can't be both. Okay. So now let's scoot on down to the last one, x squared minus 9 over x plus 3. Let's factor up top. So that gives us x plus 3 times x minus 3 over x plus 3. All right, stop here, find our domain. Domain says take that denominator and say you cannot equal 0. So if we solve for x, you'll be taking that 3 over. So x can't equal negative 3. It can equal anything but negative 3. So we'll say our domain here, negative infinity to negative 3. And then negative 3 to infinity. Now let's go back to our function up here. Let's reduce it if we can. Sure enough, here we can. Those x plus 3s are going to cancel out. So my reduced function is x minus 3. I'm going to box that in, label it up here. That is your reduced function that we'll be using as we move forward. Holes, let's go ahead and identify that. We do have a hole here, right? Because we had a term that canceled out. So since you canceled out the x plus 3, then the hole is occurring at negative 3. That's right, you're setting the x plus 3 equal to 0. So x equals negative 3. You plug that negative 3 into where? Original or reduced? Hopefully you agree, you're going into the reduced. So you plug negative 3 into the reduced function, so you have negative 3 minus 3. And that'll land you at negative 6. So I have a hole at negative 3, negative 6. Vertical asymptote, looking at your reduced function, you don't have anything left in the denominator, so you do not have a vertical asymptote. So vertical asymptote, I'll write that here for you since there is no denominator in reduced form. I'm just going to abbreviate reduced, RED. Reduced form implies no vertical asymptote. All right, horizontal asymptote. Look at your degree. The degree of the top is bigger than the degree of the bottom. So, sure enough, that means here that we are top heavy. And so since you're top heavy, you have no horizontal asymptote. It's top heavy. Let's put that in parentheses. The degree of the top is bigger than the degree of the bottom, so y. So no horizontal asymptote. X-intercept. X-intercept, remember, that's where you set y equal to 0 and solve for x. So looking at your reduced function here, setting y equal to 0, then you have 0 equals x minus 3. Add 3 to both sides, so x equals positive 3. So I cross the x-axis at positive 3. Y-intercept, we let x equal 0, and we solve for y. So here's your function, y equals x minus 3. It's your reduced function. Let x equal 0, so y equals 0 minus 3. Y equals negative 3. Across the y-axis at negative 3. All right, let's plot these points that we have here. I plot the whole at negative 3, negative 6. Negative 3, negative 6. There's our whole. I have a x-intercept at positive 3, and I have a y-intercept at negative 3. I don't have any asymptotes. Those are the points for my line here, and hopefully you're kind of making this connection. Okay, well, I just got to connect these points here. Look at your reduced function. Your reduced function is y equals x minus 3. You should have kind of recognized, hey, that's the slope in y-intercept, right? I got a y-intercept down here at negative 3, and my slope is up 1 over 1, up 1 over 1, up 1 over 1, okay? And the only thing is, in terms of, how'd that hole come in, you can't forget your roots. Where did you start from? And we started from this point, so there is this hole here in the original portion of the graph, okay? All right, well, I hope this helps. Let me know if you need anything. Thanks a lot. Bye.